Good morning children and welcome back to your chemistry class. Today in this chapter of chemical bonding we are going to talk about the covalent character of ionic bond and Fazan's rule. Now the scientist Fazan, he suggested that as covalent bonds they have some ionic character, in the same way the ionic bonds also have some partial covalent character, right? So the extent of covalent character of an ionic bond, it depends on the nature of its cations and the anions. So the percent covalent character of ionic bond, it is always determined by certain factors. What are those factors? Like for example, it depends upon the polarizing power, okay, of the cation. Then it also depends upon the polarizability of the anion. Then it also talks about the degree of polarization of anion and so on, right? So over here we shall just now try to understand what do we mean by polarizing power and what do we mean by polarizability. So firstly let us understand what is polarizing power. So polarizing power of a cation is the power to distort the electronic charge of the anion. Clear? I'll explain each and everything in detail. Try to understand what is polarizing power of the cation. It is the power to distort the electronic charge of the anion. In general, you can understand the polarizing power, it increases as cations they become smaller and more highly charged. Clear? Now let's understand what do we mean by polarizability of the anion. It is the extent to which its electronic charge can be distorted. The charge that is found on the anion, that can be distorted. So in other words we can say what? That the anions with larger size and large electric charge, they are more polarizable than the smaller ones, right? So let's understand both the things once again in detail. I would like to tell you. First, let me show you through a diagram and then I will explain it to you. Suppose this is a cation, right? And this is an anion. Okay. So over here what is happening? Just now there is no polarization. Just now there is no polarization, right? So when two oppositely charged ions of unequal size, right, they approach each other closely, right, that is during the formation of an electrovalent bond, the ion which is smaller in size, it is going to attract the outermost electrons of the other ion, right, and repels its nuclear charge. So what will happen? The net result is distortion or polarization of the bigger ion will take place. How? This cation will become smaller, right? And how has the polarization of the anion taken place? It will somehow form something like this. Okay, so this is positive and this is negative. This is your cation and this is your anion. And here we can say that this is a polarized anion. Okay. So what did I tell you? That when two oppositely charged ions which are of unequal size, they approach each other, then the ion which is smaller in size, it attracts the outermost electrons of the other ion and repels its nuclear charge, right? So the net result is what? Distortion, or what we call it as polarization, that the electrons, they are attracted towards the protons, right? So this distortion usually is done by cation. It is done by the cation as its size is smaller than the anion. So the electron cloud of the anion, which you see over here, no longer remains symmetrical. No longer it is symmetrical now, but it has elongated where? Towards the cation. So the ability of this cation to polarize this nearby anion, this is called as the polarizing power. So I have written over here what? Polarizing power of the cation. Cations, they have the polarizing power. Is this point clear? And the tendency of this anion to get distorted or get deformed or get polarized by this cation, this process is called as polarizability of the anion. So over here the cation has the polarizing power and the anion gets polarized. Okay. So this is what was explained here. So due to this polarization, sharing of electron occurs between the two ions to a certain extent, and the bond shows some covalent character as well. I hope these 2 points are clear to you. Now, the magnitude of polarization, or what I call it as a degree of polarization, it completely depends upon the number of factors or the increased covalent character, right, which is always favored by number of factors, which I am going to write it down for you just now. So all this was suggested by whom? By Fazan, and therefore now the points that I am going to talk about, they are termed as Fazan's rule. So let us talk about first point that I discussed so much over here, that is the charge on cation, right? So as the charge on the cation increases, its tendency to polarize the anion also increases, right? So as the charge on the cation increases, the tendency to polarize, its tendency to polarize also increases, right? So this brings about more and more covalent nature in the electrovalent compounds. For example, let us see NaCl, MgCl2, AlCl3. So what did I say? Charge on the cation. These are the cations. So as the charge on the cation is increasing, +1, +2, +3, the tendency to polarize also increases. Their tendency to polarize also increases. Thereby what can we say? The covalent character also becomes more and more as the charge on the cation is increasing. So this aluminium chloride has, though it is showing you an ionic bonding or electrovalent bonding, but it also has certain covalent characters which are more than magnesium chloride. Magnesium chloride also has, though shows ionic bonding, but has covalent characters also which are more than NaCl. So that is what I mean to say over here. As the charge is increasing, the polarization also increases, and hence the covalent character also increases. So over here, if you say aluminum chloride has more covalent character than NaCl or MgCl2. I hope this first point is clear to all of you. Similarly, let's talk about two chlorides like lead. It forms two chlorides, that is PbCl2 and PbCl4, right? Now what do we see over here? The charges, this over here is +2, over here it is +4. So this shows that PbCl4, it shows more covalent nature than PbCl2. I hope this point is clear. So even in variable valencies also we can decide which particular compound shows more polarization according to the charge over it, right? So in general we can say what? If a metal forms more than one halide, the halide having higher charge on the cation, right, it usually has more covalent nature rather than the one which has a lower charge over it. I hope this point is clear. Okay, we next move to the second point, that is size of the cation. Now let's talk about the size of the cation. We had discussed about the charge on the cation. Now we are going to talk about the size of the cation. So polarization of the anion, it always increases as the size of the cation decreases. Remember, okay? So polarization increases with decrease in the size of the cation, right? That is, what do we understand over here? That the electrovalent compounds having smaller cations, they show more of the covalent nature, right? For example, let's talk about lithium chloride and sodium chloride. So which one has smaller, which one is a smaller cation, lithium or sodium? Lithium is a smaller cation because as we go down the group, what happens? The number of shells are increasing and atomic size is increasing. That is, lithium is smaller in size than sodium. So what do we see? Polarization increases with decrease in the size of the lithium. So this particular electrovalent compound has more covalent nature than NaCl. I hope this example is very clear to you. Then we come to the third point, that is the size of anion. Let's talk about the size of anion. Larger the size of anion, more easily it can be polarized by the cation. Okay, so larger the size of anion, more easily it will be polarized by a cation, right? That is, what do I mean by this? That as the size of the anion increases for a given cation, then the covalent character also increases, right? So let's take an example over here. Like for example, let's take lithium fluoride, then lithium chloride, we can take lithium bromide and lithium iodide. All we can say they are showing ionic bonding. Now which particular ionic compound has more covalent nature? So let's read here. Larger the size of the anion, right? More easily it can be polarized. Larger the size of the anion. Now fluorine, chlorine, bromine, iodine. Which one is larger? Iodine is larger, right? It can be polarized by a cation. So this will get more polarized than lithium bromide, than chlorine, and least will be that of fluoride. Clear? Let's take one more example of, say, calcium fluoride. So it is CaF2, then calcium chloride, then calcium bromide and calcium iodide. Okay, so over here also, of all the calciums, iodine has a larger size, so this will get polarized more. So this is going to have maximum covalent nature. This electrovalent compound is going to have maximum covalent nature, followed by calcium bromide, then calcium chloride, and least will be that of calcium fluoride. I hope all this point is very clear to you. Okay, now let's talk about the fourth point over here, that is the configuration of cations. It also depends upon the configuration of the cations. That is, the cations with 18 electrons in the outermost shell, they bring greater polarization of the anion than those with the inert gas configuration. Even if both the cations, they have the same size and the same charge over it. Clear? I repeat, what did I say? That the cations with 18 electrons in the outermost shell brings greater polarization of the anion than those with inert gas configuration, even if both the cations have same size and same charge. Okay, so let's take an example. Let's talk about copper chloride and sodium chloride. Okay, so over here let's talk about copper ion. Now over here, which copper ion am I using? I'm taking this example up somewhere here. So look over here, copper ion is plus. Okay, so configure it is 2, 8, 18, right? So the size of it, of the copper ion, is somewhat 0.96 Armstrongs. Now let's talk about sodium ion. Then over here we will see the configuration is 2, 8, right? And the size of this particular ion, it is somewhat 0.95 Armstrong. So what did I say? The cations with 18 electrons in the outermost shell. Which one? This copper ion brings greater polarization of the anion. Greater polarization of the anion than those with the inert gas configuration. Even if both the cations, they have same size and the same charge over them. I hope this point is clear to all of you. So in general, what can we say? That all electrovalent compounds, they have high values of polarization, or we can say they have more covalent characters, right? They are found to be less soluble in water, but they are more soluble in organic solvents also. This is one important point that you need to remember, that all the electrovalent compounds which have more covalent character, they are found to be less soluble in water, right? But they are more soluble in organic solvents. I hope this point is clear. So in general, try to understand that on moving down the group, okay, on moving down the group, what happens? The polarizing power of the cation goes on decreasing because the size is increasing. Whereas what is written over here, polarization increases with the decrease in the size. So as we are going down, the size of the cation is increasing, therefore polarization will decrease. Then the polarizing power of the cation, it increases when we move from left to right in a period, right? And polarizability of the anions by a given cation, it always decreases in moving from left to right in a period. And polarizability of the anions by a given cation, it always increases from top to bottom in a group. Then last point, the increase of polarizability, it brings more of covalent character in an ionic compound. This point is very important. You should remember. So the increased covalent character is always indicated by the decrease in the melting point of the ionic compounds. So we can say that the melting point also decreases. Melting point decreases as we move from left to right. I hope this point is very clear to all of you. So polarization is also increasing, covalent character increases, and melting point decreases as we move from left to right. And from top to bottom, what happens? That the polarizing power of the cation goes on decreasing, but the polarizability of the anions by a given cation, it increases from moving from top to bottom. So this was all your Fazan's rule, right? So with this we finish off with the covalent bonding. Now we are going to move to the coordinate bonding. So let us begin with coordinate bond. It is a special type of covalent bond, you already know, in which both the shared electrons, they are contributed by one atom only, right? So how can we define what is a coordinate bond? It is a covalent bond in which both the electrons of the shared pair, they are contributed by one of the two atoms. So to begin with the coordinate bond, it is important that in the covalent bond, the particular atom should have lone pairs, right? So this bond is also termed as what? It is also called as dative bond, right? So a coordinate bond, or what we say a dative bond, it is always established between two such atoms where one of which has a complete octet, right? And it possesses lone pairs, what we can say, while the other is short of pair of electrons. Okay, so over here there is a donor, the atom which donates the pair of electron, they are termed as donors, whereas the atom which is short of pair of electron, it accepts the electron, and they are termed as acceptors. So here we have the donors and here we have the acceptors, right? So over here the formation of the coordinate bond, it can be more looked upon as a combination of, you can say, electrovalent and covalent bondings, right? So it can take place in two steps. What are those two steps? First, the donor atom, it loses one electron, which is transferred to the acceptor atom, right? And what happens over here? Then the donor atom, it acquires a positive charge, and the acceptor atom, it acquires a negative charge over itself, right? For example, you can say like this is A, C, and it combines with B, which lacks electrons, pair of electrons. So what will happen? This is going to donate 2 electrons and it is going to form a positive charge over itself, and this accepts one pair of electron and attains a negative charge over it. Okay, so these two charged particles, they now contribute 1 electron each, and this pair is shared by both the atoms. So over here, as the coordinate bond is a combination of one electrovalent bond and one covalent bond, it is also termed as a semi-polar bond because both the charges are present over here. So this compound consisting of coordinate bond, this is called as a coordinate compound. This will be termed as what? A coordinate compound. Now we are going to do certain examples to understand. The ones which you have already done, that is the formation of ammonium ion, you have done before. So over here, let us first draw how do we form ammonium? Ammonia combines with a proton, right? So let us first draw the structure of ammonia. This is the structure of ammonia, right, which has a lone pair, and this is your proton, which is deficient of electrons. So this ammonia, nitrogen, it donates its pair of electrons, right? So this is a donor and this is your acceptor. And what it is going to form then over here? Nitrogen H, and since this lone pair is being donated, so it has to be shown with an arrow, right? And then we write H, and this becomes a ion. A positive ion is formed over here, right? Now let's take another example of hydronium ion, HO plus. This is A, this is B. How is this formed? Water combines with a proton, right? So let's first draw water. Water is H, OH, right? This is the covalent bonding shown for water. It combines with a proton which is deficient of electron. So what will happen? This oxygen, it has two lone pairs. It is going to give away one lone pair to only one lone pair to this proton, and hence what it is going to form? A coordinate bond, that is H, O, H, and this is donated to hydrogen, and one lone pair is present over here with a positive sign. Okay, I hope this point is very clear to all of you. Okay, then let's come to another example. Formation of H2O2, right? So oxygen in water, it has two lone pairs. We already know that, right? Out of which one is donated to another oxygen atom, which forms the hydrogen peroxide. So over here, in fact, H2O plus O is going to form H2O. So let's do it over here. Now this one I can also draw like this, H and H. It can be drawn like this also, okay? And these are the two lone pairs. It combines with oxygen. Now this oxygen has how many valence electrons? 1, 2, 3, 4, 5, 6. It is deficient of pair of electrons. So suppose this pair of electron is donated to this oxygen. So what it is going to form now? It is going to form H, O, this is H, and this is being donated, so this is O, right? So this is the structure of what? Hydrogen peroxide. H2O2 will be formed like this. Okay, let's talk about another example, D, formation of ozone, O3. How is this formed? So let's look at oxygen molecule. Oxygen, what is the valence electrons? 1, 2, 3, 4, 5, 6, isn't it? 1, 2, 3, 4, 5, 6. So like this they are combined. Clear? Then this oxygen, that is O2, how is it formed? O2 plus O. So combines with oxygen 1, 2, 3, 4, 5, 6, right? And this oxygen, which has a lone pair, donates it to this oxygen atom, and thus the structure formed will be oxygen combining with another oxygen with a double bond, and there it gives away the lone pair to one oxygen atom. So this forms your ozone, that is O3. Okay, let's talk about some more examples. Now let's talk about another example like formation of carbon monoxide. Carbon, what do we know about this carbon? It has 4 valence electrons. So 1, 2, 3, 4. And oxygen, it has how many? 6. So 1, 2, 3, 4, 5, 6, right? So both combine to form a double bond and a coordinate bond to achieve their octet completely, right? So how does that happen? This becomes your acceptor and this becomes your donor, right? And thus it is going to form what? With a double bond with oxygen, and here it donates its pair of electrons also to carbon. So this forms carbon monoxide. Okay, then let's talk about nitric acid. EFHNO3. So coordinate bond is formed in the nitric also. How? Let us look over here. Oxygen with 6 electrons. Okay, 1, 2, 3, 4, 5, 6. And nitrogen with 1, 2, 3, 4, 5. Okay, and oxygen how many? 3. So I have just made 1. Now 1 over here and 1 over here. So this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now let's see, one hydrogen is left. Okay, let me draw hydrogen over here. So firstly let us see this. This is 1, 2, 3, 4, 5, 6, 7, 6, 7 and 1, 8. Okay, let's talk about nitrogen first. 1, 2, 3, 4, 5, 6, 7, 8. So its octet is complete, right? Now these are the two lone pairs that nitrogen has. So these two lone pairs are given to this oxygen. Okay, let me draw it like this. Right? So now 1, 2, 3, 4, 5, 6. They are donated to this oxygen. Is this point clear? Now this is understood. Now let's come this side. This oxygen 1, 2, 3, 4, 5, 6, 7 and 1 can be donated to oxygen over here. This becomes your acceptor. So this is your structure of HNO3. So it can be formed like this, like N double bond O donates it to this, oxygen needs to hydrogen, right? So two coordinate bond, one nitrogen with a double bond, nitrogen with a single bond with oxygen. So this is the formula of your nitric acid. Now let's take one more example, F, then G. Okay, so over here I'm going to show you combination of ammonia and boron fluoride, that is BF3, right? Now although we know that the nitrogen atom has complete its octet in the ammonia and it has still how many? One lone pair of electron in this shell which it can donate. Now let's talk about boron fluoride. Now over here boron atom, in boron fluoride it is short of 2 electrons, right? So it accepts from where? From that nitrogen and hence shows the coordinate bond. How? Let's see this. So nitrogen, let's draw ammonia over here first. This is the structure of ammonia. Clear? Now let's look at BF3. B, F, F and F, right? Where it is short of 2 electrons. So this becomes your donor and this becomes your acceptor, right? And what it is going to form? Look here, H, N, H and H, and this is donated to B, F, F and F. Clear? So this is your coordinate compound. So any atom or ion or molecule which has one unshared electron pair which it can donate. They are termed as what? Lewis base. So over here ammonia is called as a Lewis base. Okay, it is termed as a Lewis base, while those which are capable of accepting the lone pairs, what are they termed as? They are termed as Lewis acids. So acceptors, they are Lewis acids, and donors, they are Lewis bases. I hope this point is very clear to you. So with this we finish off with the coordinate bond also. Thank you for today.